9. Introduction to t-testing. Okay, so this lecture is going to feel a lot like z-testing. The flow, the function, there's just a slight difference. Okay, so definitely think back to z-testing throughout this whole lecture. So some of the things we'll be going over today are know when to use t versus z, how to perform hypothesis testing with t-testing, and then how to evaluate things like effect size using Cohen's d, percentage of variance accounted for, r-squared, and then a little bit of confidence interval, but we'll touch into that a little bit more in t-testing. So this is like a 3-part series with t-testing. So in the second and third lecture series of, or the lecture videos of this series. Okay, so some things to keep in mind. Definitely standard deviation, degrees of freedom, standard error, and then hypothesis testing, which we spoke about in the last lecture. Okay, so T versus Z is just an alternative, right? So we hit Z testing quite a bit in our last few lectures, right? So we just take again the sample mean, the estimate, and approximates the population mean. And then again, this whole idea of standard error describes how much difference is reasonable to expect when we take a sample mean and then we try to approximate or infer back to that population mean, right? So we have this sample mean, okay, but we did something to it, right? We gave it a meta-centered treatment, and then we say, okay, how much can we really infer back to that population that our treatment was effective? And you have a couple different equations down there describing like this whole idea between sample mean and population mu. Okay, so the z-score statistic really is useful to quantify inferences about the population. And again, you have your z equation there, right? So z equals mean or sample mean minus mu, the population mu, divided by the standard distance or between the sample and the population. And you can use that unit normal table, your z table, to find that critical region. And if you find that your sample group, right, fell in that critical region, you can say, yay, my critical value of z, my obtained, fell in that critical region, and I can reject that null hypothesis. And I can use that unit normal table as long as I'm grabbing a sample, a group over 30, right? Because 30 is our magic number there. Or I know that I'm grabbing that original, I'm grabbing it from a population that I know is normally distributed. Well, and that's the crux of the thing, right? How do I know sometimes, or know by without a shadow of doubt that I'm grabbing from a population that's normally distributed? And that's why we use the T. All right, so the problem with the Z's are the Z requires a lot of information, more information that researchers typically have available. When we talk about things like blood pressure and IQ scores and GRE and SATs, we have a lot of information. When we're doing research, we're usually doing research on concepts, ideas, on things that we don't have a lot of information about. So this requires knowledge of the population, standard deviation, right, that beautiful Greek letter O with a little curly Q on top, that's needed to compute the standard error. And researchers usually only have access to or availability to sample data, which then excludes us from being able to use that unit normal table. Which then allows us to use then the T statistic, right? So T then is the alternative to Z. And if you want to think of it like T allows us to approximate the Z, right? Or the estimated standard error, S sub M, is used to estimate the actual standard error of standard error. So the again, sigma or the standard deviation M, right? When the value of the actual standard deviation is unknown, right? It's computed from the sample variance or the standard or the sample standard deviation. And it really does allow us, the researchers, an estimate of that standard deviation or distance, right, between the sample mean and the population mean. So how far can we estimate? How far can we assume or guess, right? Is our sample mean from the population mean, right? How far away does it deviate? How far away in distance-wise is it from the population? Okay. So estimated standard error, how do we get that? Well, there's a formula for that. So estimated standard error, and again, the symbol, the shorthand, mathematically we use S and then sub M, right? What that is standard deviation, right, for a sample, divided by the square root of your sample size. Or if you just want to take the square root of variance divided by your sample size. Okay, so when the value of your standard error is unknown, we use the estimated standard error. Because again, when we know a lot about a population, we can use Z. When we know standard deviation, when we know population mu, absolutely go with Z. When you're running a new teaching methodology to get people to score really, really high on an IQ test, right? We have millions of data points on IQ test, run the Z. But if you're running a new teaching methodology on how to get second graders to, I don't know, fall in love with fiction or nonfiction books, right? You don't have millions of data points. So you don't know the population standard deviation. You don't know the population mu. You're going to have to do more of an estimated standard error. And that's where the power of the T comes in. Okay. So use estimated standard error to estimate standard deviation. Okay. So the T statistic uses estimated standard error in place of, right, these known things, these known parameters that the Z statistics will give us. So here's our new equation of not just of this lecture, because like I said, this is kind of a 3-part lecture. So with this one is the introduction to T statistics, and then we also have 2 more videos that will follow up with this one. So this one is the one for this lecture, right? And this T statistic is used to test hypothesis about an unknown population, right? Mean, or mu, sorry, I shouldn't say mean, but when the value of the standard deviation is unknown, which again is the bulk of research. Most of the time we don't know a lot about the population that we're studying, or to be frank, we wouldn't be studying it, right? Okay. With degrees of freedom, I don't know if we've discussed degrees of freedom before, and this with T-scores will stay the same. It will change with later videos in this series, but right now degrees of freedom is just n-1. Okay. It's a computation of sample variance required that is allowing the scores within your sample that's independent and free to vary. So maybe we have talked about this a little bit in previous ones. So we're just digging a little bit deeper into it. So researchers call n-1, or your sample size -1, the degrees of freedom. Again, so if your sample size is 30, right? So if you're getting that great golden number of 30, at this stage in our development of statistics, your degrees of freedom is 29, or again, DF equals 29. So degrees of freedom is the number of scores within your sample that are independent and free to vary, one being kind of locked in or not able free to vary. Okay, so a T distribution is a family of distributions, so it's a grouping, one for each possible number of degrees of freedom. And yes, it does approximate that shape of a normal Z distribution. It's not exact, okay? It's a little bit more spread out in its shape. So if a Z distribution is that more perfect bell curve, right? That more normal distribution, right? The right? the T takes that normal distribution and kind of goes, right? So the tails are going to be thicker. There's going to be more variability, so the scores are going to be more scattered all over the place, okay? And the groups of score are more spread out than what we would see in a more Z distribution, okay? We also have a new table. So we use a T table instead of the unit normal table because there are those unknowns. We don't know the population mu. We don't know the standard deviation because we don't have those millions of data points. And that's okay because, again, we're doing research. We're doing research on the unknown, and that's great, right? That's needed. So now we're going to use a t-table, and you can find that on the Google, right? You can find it, you can look it up, in place of that unit normal table. And yes, we are going to do hypothesis testing, so that same skill set you learned in the last lecture, please still use that. This is what it looks like, right? Okay, so again, that normal distribution, that bell curve, same kind of look, it's just squatter. It's just like someone sat on it, right? So distribution of the t-statistic, what you see here for different values of degrees of freedom, okay? And again, your degrees of freedom are set on how big your sample size is. So you can kind of, you can manipulate the shape of it by increasing or decreasing your sample size, okay? So what you see there is distribution of the t-statistics for different values of degrees of freedom as compared to a normal, just standard z-score distribution, okay? So the top one there is that normal distribution, that z normal distribution, okay? The second one, right, the kind of one in the middle there, is a t-distribution with degrees of freedom of 20. So you pulled 21 people to be in your sample, okay? So you see how it kind of dropped a little bit? And then take a look at the tails. The tails got thicker, squatter, okay? So like the normal distribution, the t-distributions are bell-shaped. They are still symmetrical. Whatever's happening on the left-hand side is also happening on the right-hand side, okay? And, however, the t-distributions are more variable. Just like we said in the distribution of sample means, we're not talking about one score. We're talking about groups of scores, okay? So the t-distributions are families of scores. They are groups, right? They are chunks. They are samples. So t-distributions are more variable. Their scores are more widely scattered within there than a normal distribution, okay? And that's indicated visually, you can see it, by the flatter and more spread out shape. The smaller your sample size, so you can see there with a t-distribution of 5 degrees of freedom, so now your sample size is only 6, right? It got even shorter, it got even more squatter, okay? So the larger the value of degrees of freedom is, the more closely it's going to approximate that normal distribution, okay? So if it's very, very small, it's right? And then as it gets bigger and bigger and bigger, your sample size, right, it's going to approximate that more beautiful, perfect normal distribution, okay? So sit with that for a second. That should make sense, right? Because the closer I get to pull to the normal distribution, to my total number of people in the population, if I keep adding more and more people to my sample size, well, yeah, I'm going to keep adding more and more people till I get to the samples, till I get to the population size. I'm not going to have an error. It's going to be perfectly mirroring the population, okay? So this one is t-distribution with 3 degrees of freedom. So the 5%, right, because we have a two-tailed test, we have to split the tail, right? So 5% distribution is located in the tail beyond, so T is 2.353. So anything in the tail beyond positive 2.353, or anything beyond the tail negative 2.353 is going to still fall in that critical value region, just like our Z did, and you're going to reject the null hypothesis. Okay, so in this one, sorry, it's wrong. So in this one, you have proportion alpha set at 0.1, so 10%. So if I split it in 2, I have 5%. So I have 2 critical regions at 5%. If I combine the 2 tails, I have 10%. Right, so I have 10%, I split it in 2, I have 2 critical regions at 5%. Those are 2 pretty big areas I'm giving myself to hit the critical region. So if I run my numbers and I get a T obtained of anything less than negative 2.353, so if I run my T equation and I get a T obtained of negative 2.4, I can reject my null. But if it falls in that non-peachy middle zone, that middle 90%, if I get a t of negative 1, positive 1, positive 2.2 even, I have to fail to reject. If I run my t and I get a t obtained of anything more than positive 2.3, so I get t obtained plus or positive 2.4, I can reject my null hypothesis. Okay, because what I'm saying is, I'm not proving it, but I'm saying that my little group of 30, 40, 100, whatever my sample size is, in this one, 4, right, a small sample, I did something to them. I gave them a medicine. I did a treatment on them. I made them do a certain protocol. Had them watch a movie, had them do a certain exercise, whatever I did to them, right? I manipulated that independent variable. And those 4 people in my study, together, their average, because again, a t distribution is a family, it's a group scores. Their average fell so far much higher or lower, depending on how you want to say it. This is a two-tailed test. That it's statistically significantly different than that middle 90%. I'm rejecting the null hypothesis. Okay. So again, here's your linguistically what it looks like or what it sounds like. So what you're doing is you're taking the sample mean, right? Your little group of people. What's their average? You're comparing that. How far away from the population mean did they fall? Now, you're not dividing it by the standard deviation because we don't know a lot about the population. And that's the only difference between a t and a z. Now you're dividing it by the estimated standard error. And that's going to give you your t crit, or your t obtained, sorry. And then you're just going to compare that to your critical region, your t crit. Okay? This is just it graphically. So let's assume that the parameter mu, so the population mean, is known. But in most studies, it's unknown. So the purpose of the research study is to determine whether your treatment has an effect. Okay? But in most research studies, a lot is unknown. A lot is unknown about the population mu, standard deviation. So we're still going to run it like a z-score, but using the t equation, we're going to approximate a lot of things. Okay? We're still going to run it just like a z-score. That means we're still going to run it with a hypothesis test. You're still going to state the null and alternative hypothesis, set the alpha level. In social behavioral sciences, that alpha level is usually always 0.05. Just like in previous lectures, when you set the alpha level, what you're also doing is saying, okay, that's going to tell me what my critical region is. Okay, so if I say my alpha level is 0.05, it's a two-tailed test, look in my t-table now, not my unit normal table, my t-table now. Tell me what my critical region is. Tell me what my archery ring is that I have to hit, right? And then run your test, right? Collect your data, run your analysis, calculate the t-statistic, use that new equation I gave you, right? Once you have your t obtained, compare it against your t-crit. Use a t-table, and then make your decision. If your t obtained falls, right, within that critical region, you can reject your null hypothesis. You rejected nature. You manipulated that independent variable so much that your group, you're not saying you proved anything, but you're saying it's highly improbable that they just randomly fell that far out of norm. You can reject the null hypothesis, so make your decision. But if your group falls within that normal region, you fail to reject. Just like we did with z-testing. So again, like we started the lecture, it should feel very, very similar. Okay, so again, this is alpha level set at 0.05. You have 8 degrees of freedom. Set your critical regions. It's a 2-tailed test. See your critical regions there? So you have 2. So if I run my t-test and my little group falls, on average, if they give me a t obtained anything less than negative 2.306 or anything greater than positive 2.306, I can reject the null. I did it. I rejected the null. I manipulated that independent variable enough to move them as a group in a statistically significant way. But if they fall in that middle 95%, I missed the mark. I failed to reject the null. Okay, some of the assumptions. The value in the sample must consist of independent observations. You can't double dip your people, right? And the population sample must be normal. Okay, again, when the sample is relatively large, the assumptions can be violated without affecting the validity of the test. So when in doubt, pump up your sample size. Yes, I know, that's easier said than done. Okay. Some of the things that influence your goings on with your research study. Number 1, your sample size. Okay. The larger the sample size, the smaller the error. So again, increase your sample size, you're going to decrease your errors. Also, the larger the variance, the larger how all over the place your scores are, it's going to increase your error. Okay, so large variance means that you're less likely to obtain significant treatment effect. Okay, so try to reduce the likelihood of having scores being all over the place without manipulating your data. Okay. Effect size. We're going to stick with Cohen's d. Okay. So hypothesis test simply determines whether the treatment effect is greater than chance. Let me say that part again. Hypothesis test simply determines whether my treatment effect, what I did when I manipulated that independent variable, is greater than just chance. Okay? And chance, in statistical terms, is measured by standard error. So no measure of the size of the effect is included in the hypothesis test. So you have to do it as like a separate part of your analysis. Okay, and again, please keep in mind that a very, very small treatment effect can definitely be statistically significant. So absolutely similar to z-scores, you need to run a report on effect size after you run like your hypothesis testing. And again, we're going to stick with Cohen's d. So the original equations, including the population parameter, again, the population mean with treatment and standard deviation are both unknown. We know this is why we're running a t-test instead of a z-score. And Cohen's d is still going to be that 0.2, 0.5, 0.8 small, medium, large-ish effect size. Again, these aren't thresholds that we're looking for. You don't have to get to 0.2 to say it's a small effect. If it's 0.4, say medium. Again, you're looking, what Cohen's d is saying is what's the mean difference? What's my sample minus my population? How far away is that? Now, instead of standard deviation, because I don't know it, it's that sample standard deviation or estimated. So instead of saying Cohen's d, I have to say now estimated Cohen's d because I'm running a t instead of z. It's fine. What you're still saying is I'm running a hypothesis test, and in my reporting, in my results, I'm going to give you now also the effect size. as estimated Cohen's d. Okay. Another way you can say is you can say, I'm going to give you the percentage of variance accounted for, or percentage of variance explained, R2, okay, or R squared, okay. Also great. Alex Cohen's d, you can use percentage of variance explained or percentage of variance accounted for, okay. With these, 0.01 is small, 0.09 medium, 0.25 large. Again, these are not thresholds, these are ranges. So if you get 0.1, say medium. If you get 0.15, sure, say medium. If you get 0.19, make a call. I would say large. You can say medium. Say both, though, in your reporting. Say 0.19, medium, 0.19, large. It's okay. What you're trying to say is, in addition to my hypothesis test, I also am giving you the effect size. I put the equation down there. Whatever your t obtained is, so t squared divided by t squared plus your degrees of freedom. Again, the math isn't that hard. What I really want you to do is understand more so, what are you doing? What you're doing is you're measuring effect size. Regardless of sample size, isolate that independent variable. How effective is it? And again, this is just another example or graphic of a distribution of t statistics for 8 degrees of freedom. Sorry. Okay. If your family of, because I'm trying not to say distribution of sample means, because that's a z. So if your group, if your sample, if your family of that you did a treatment on falls into that middle, you fail to reject. Okay. If it falls in one of those critical regions, do a little happy dance, right? You reject that null hypothesis. Okay. Okay. Reporting. So 1, report whether it's significant or not, right? So did you reject your null hypothesis, or did you fail to reject your null hypothesis? When you say you're rejecting your null hypothesis, what you're saying is it's significant. My results are significant, or my results are not that significant. 2, report your t obtained, okay, including your degrees of freedom. So what you would say is t, and then whatever your t, right, degrees of freedom. So in this case, you would say t and then 8, so I have 9 people in my study, equals negative 2.67. So my negative 2.67 is my t obtained. So like when I run my t equation, that's what I'm telling you. Okay. And then you can also report your significance level. And then what that looks like is usually the p-value. And again, you don't have to run it manually or by hand anymore. Your software will tell you that. Okay. Same thing with Z. You can run a one-tailed test. Most of the time you're running a two-tailed test. Usually with a non-directional, it's social behavioral sciences. Usually, like I said, 99% of the time it's a two-tailed test. You can do a directional or one-tailed test. If it's a pilot study, usually with ethical concerns. Same 4-step hypothesis testing like procedure though. The only difference is it looks like this, right? So you're going to shove all of your critical region into one side. That's like the only difference, right? You're not going to split your critical region, right? So if it's alpha 0.05, that whole 5%, if you will, is going to be in one side. Okay. That's pretty much it for t-testing. It's great because it allows us to use everything we've used or learned so far about Z and about hypothesis testing, and we can use all of that in the hypothetical, I don't know a lot about this population I'm studying, right? It allows us to like kind of branch out now and start talking about everything besides IQ testing and GRE and SAT. I love that stuff, and there's so much more out there to study besides just IQ and GRE and SAT.